Ready? Wish we had a regular chalk.
All right, we'll go ahead and get started. Thank you for coming. It's 12:15 and we are streaming this, so Erik will look every now and then how many people are on there so I can get a count. They don't get snacks, so, and they don't get the door prize. So it's better coming, so thank you.
All right, so I thought I'd start us off with a little intro problem today. I passed it out, I don't know if you've worked it, but let's read it real quick. Mrs. Bridencamp's daughter, whose real name was Colleen, set out to deliver jam and jellies. First she stopped to see Mrs. Parsley, who took in Grandma's mail while Grandma was at the hospital recovering from the wolf. Colleen gave Mrs. Parsley 1/3 of the jars in her basket. When Colleen set out again, suddenly the wolf jumped out from behind a bush and grabbed 1/2 the jars in her basket. After the wolf ran off, Colleen went on and gave Mr. Woodsman 2/3 of what was left in her basket. She thanked him for getting the Grandma out of the wolf and started off for Grandma's house. Colleen had 6 jars and jams of jelly left for Grandma. How many jars did Colleen leave home with? All right, I'd like you to spend about a minute just trying to solve this problem. You have the skills to solve this problem, and I'll just let you try to solve it however you want.
Don't want to. No, I feel no.
All right, so we'll come back to this problem in a little bit and go through the solution. I was just curious how you would approach the problem, and we'll talk about problem solving in general. So, all right, so this is how to solve it. A presentation on George Polya's problem solving method. George Polya was a pretty famous mathematician. I'm Chuck Newberg, professor of mathematics. And let's dive into this. I forgot to bring the book, so I was supposed to hold the book up right now. It's a pretty famous book that I read. It's always been on my bucket list to read, and I finally got around to reading it. And so which was always kind of glad I did. So George Polya, 1887 to 1985. So he was around during my lifetime. And I know he had a major influence on my math education. He's a mathematician known for contributions to problem solving, heuristics, and combinatorics. And we're here to talk about his problem solving skills today more than anything else. So he developed a systematic approach for solving mathematical and real-world problems. So this is the
What is heuristics?
Heuristics is an interesting It's a type of problem solving where you generalize things. It's an interesting, I had not studied heuristics before, but he like generalizes statements and draws conclusions. So your conclusions are not always necessarily guaranteed to be absolutely right, but it's what happens if you generalize these things and what can you conclude from them.
So it's more logic.
It's more logic, yep. And I was going to say, if you want to know more about heuristics, I did not know about heuristics. I'd seen the term before. But if you want to know more about it, I recommend Googling it and reading it. You'll find out it's a fascinating area of mathematics. So, all right. So he came up with the 4-step problem-solving model. And his model was understand the problem, devise a plan, carry out the plan, and look back. 4 basic steps. And what you do in those steps is the crucial part. So he's like known for like the father of problem solving because he said, hey, we need to streamline these steps, get it down to where we can help our students become better problem solvers. So step 1, understand the problem. So before attempting to solve a problem, it's crucial that you comprehend the problem. You got to know what the problem involves. So what do we do with this step? Well, first off, we identify what the given information is and what is the unknown. And so often when I have students come in and ask me a question, if I ask them what we're looking for and they tell me, then they run off because they've figured out how to solve the problem. But if you don't know what you're looking for, it's hard to figure out how to solve the problem. So ideally, you go through and identify what's given. I like to write it down. And I noticed as I walked through the class here, a lot of you wrote down the given information. You wrote down a little bit of this, you wrote down a little bit of that, and that was the start of good problem solving skills. So then you restate the problem in simpler terms. And some of you might have tried to rephrase it. And you might have even looked at, was this a problem I've solved before? And anybody draw a picture? Just out of curiosity, no pictures? Not one picture on this whole problem? All right. So you can organize the information with graphs, sketches, and tables. So in step 1, it's important you identify the given information, what you're looking for, and really start drawing pictures and restating the problem into something that you can understand, make it a little simpler. And he spent quite a bit of time in the book reminding you to pay attention to definitions, because definitions are the building block of your terms, and sometimes they hide the key concepts. So he really emphasized paying attention to the definitions. If you have a problem that you don't know the definition, maybe you look up the definition and write it down so that you have it sitting there in front of you so you can use that definition to help you solve the problem. All right, so to me, step 1's the foundation. If you don't know what you're looking for, you can't solve it. If you don't identify the given information, you're going to struggle to solve it. If you don't draw the pictures and do the tables and stuff like that, you're going to struggle to solve it. So this step ensures a solid foundation before moving on and planning a solution. All right, step 2, devise a plan. Here we come up with a strategy, and we're choosing a strategy. And in the book, he talks about 18 different strategies, although I suspect now with computers and stuff like that, it would get expanded on. Because computers have added into our problem-solving skills. Restating the problem, relating the problem to previously solved problems. Every problem you solve should be in your bag of tricks to use later for future problems. So, and you just build up this big bag of tricks of problem-solving skills and use them to solve other problems. And I imagine most of you probably used fractions, and you relied on previous problem-solving skills on this problem right here. All right, formulate step-by-step actions. Now, sometimes I don't sit there and think about each individual step unless it's a complex problem. I can guarantee you when I remodeled my bathroom, I thought about every individual step because I was nervous because that's not in my problem-solving skill set. So I really had to get into step 1, understand the problem, before I, step 2 started tearing into my bathroom. So, all right. And a well-devised plan increases the chance of solving the problem efficiently. So you go from understanding the problem to thinking about it briefly. How am I going to solve this problem? And then step 3 is where we actually get our hands dirty. Oh, I forgot we have this slide here. So here's a partial list. I did have all 18, and I decided 18 was too many to look at. So let's look at a partial list of strategies. Draw a diagram. Pictures always help. Introduce suitable notation. Start labeling things. If you have a length, call it L. If you have an area, write it down as area equals 52 or whatever. And so start introducing notation. That will help you introduce equations if you need to use an equation. Step 3, work backward. Sorry. Technical difficulty, TV land. All right, sorry if you couldn't hear me out in TV land. So I get excited sometimes. Work backward. Did anybody try working backward on this problem? Yeah, some of you tried working backward. Yeah, this was a classic problem to work backwards. You just had to be patient about it. Breaking the problem into parts. When I do finance problems in my problem solving class, we tend to break problems into parts because each part has its own little chunk of interest to be added together. All right, so breaking things down into parts, we'll do a problem with that. Consider analogous problems, problems you've already solved before. You might reuse that same solution to help you solve this current problem. So the Pythagorean theorem is a classic example of that. Work with equations. A lot of mathematical problems do involve setting up and solving equations, which is important why you need to introduce suitable notation as well to help you set up your equations. And guess and check. Now your teachers may not like that, but guess and check is a valuable approach, especially if you don't have anything else going on. Maybe guess the answer and see if it works. But in guess and check, the key thing is not only you have to be able to guess the answer, you got to be able to check it. And not every time can you check it without trying a different approach. So guess and check, while it's a great approach, it has its limitations. You got to be able to check. All right, step 3, carry out the plan. This is when we actually get our hands dirty. So we figured out I'm going to use an equation. And then you set up your equation and solve it. So this is when we, after devising the plan, we introduce this, we implement the steps systematically. We go through and executing the chosen method carefully. So we don't want to be sloppy about it. We want to be organized and go through step by step and try to implement our plan. And if we do that correctly, we should come up with a solution. And keep track of your calculations and your reasoning. And be patient and persistent. Sometimes you got to be really persistent on a problem. Just don't punt on the first try. So, and check for logistical consistency. And modify the approach if necessary. So you started down, you picked a plan, and you started down that plan, and you realize your plan sucks. You realize it's not going to work. Well, what do? You might go back to step 1, see if you're misunderstanding something about the problem. You might go back to step 2 and think about what's a different plan. And so, all right. Sorry, I thought I was getting a signal there. So, all right. So you might go back and see if you need to redo a different strategy or see about understanding something else in the problem. So the key to this, the key to success in this step is accuracy and flexibility. You got to be willing to change your plan. You got to be willing to go back and look at step 1. All right, then step 4, look back. Once the solution's reached, it's essential to review the process and results. So after I work a problem, I often like to look at it, especially if it's a good complicated problem, and look at it and say, could I solve that easier now that I've brute force this problem this way? Could I found a better solution, an easier route than the route I took? Could I use this strategy to help solve another problem? And can I generalize this? So there's a lot to do on step 4. besides the fact celebrating you got an answer, verifying the solution, make sure you actually answered the question. Sometimes you do all the work, but you don't actually answer the question. You find the width of the rectangle and you needed what? The length of the rectangle, and that's a simple fix. So you always want to make sure you solve the problem and verify your solution. You look at using a different method now that you've solved it, and interpreting the results. Make sure the results make sense. If you have me running 30 miles an hour, the results don't make sense. All right? You have me jumping 2 inches high, the results make sense. All right. And learn from the process. I mean, after all, you're developing problem-solving skills. Learn from that process. Often when I fail on a problem, I look at failure on a problem as a success as well, because I look at what doesn't work and why it didn't work. And then I learn from my problem-solving skills and add into my bag of tricks. So, all right. And, all right. So, applications. So, this is used in mathematics, science, engineering, and daily life. Guess where else it's used? It's a hot new subject, AI. They are using Polya's 4-step problem-solving model in at least one AI group is using it to help AI learn how to solve problems. So they're trying to teach the computer how to solve problems using these same 4 steps. So encourages logical thinking and systematic problem solving. When I get stumped on something in class, and it happens more often than I'd like to admit to, I go back to the 4 steps. My students might be thinking I'm just writing down the information for them. The reality is I'm writing down the information for me, because I'm stumped on that problem. I'm still writing down the given information, thinking about my strategy. And then usually the light bulb turns on and the strategy pops up after I've written down the given information and identified what I'm looking for. So it's amazing if you just write down the given information, clearly identify what you're looking for, how often the light bulb will turn on, and you're like, oh, I know how to work this problem now. I remember working a problem similar to this before. And helps improve critical thinking and decision-making skills. I mean, you have to have something, and if you think about it, there's nothing more basic than the 4 steps. Understand the problem, devise a plan, carry out the plan, and look back. You could maybe skip step 4, but that's just not good problem-solving skills. But the first 3 are fundamental to solving any problem. All right, so let's go to this problem. First off, this is a 5th grade math problem. So, 5th graders do not have fraction, multiplication, nor division. So, I can't multiply, nor can I divide. All right, so let me go through and understand the problem. So, step 1, understand. Well, I understand that Mrs. P gets 1/3. The wolf gets 1/2. Mr. Woodsman gets 2/3, and that's what? 1/3 of what's in the basket, 2/3 of what's in the basket, and so forth. And I'm looking for and then we ended with 6. And I'm looking for how many did she start with? Okay. If you try this problem with Turnitin, they will use algebra. We don't need algebra. Step 2, divide the plan. I am simply going to draw a picture. All right, this is all we need, is just a picture. So step 3. Let's draw a picture. Okay, so here is the basket of goods. jars and jams. So we go along. We run into Mrs. Parsley. She gets what? 1/3. Now they do understand basic fractions. So they understand I can divide this into thirds, and Mrs. P gets this right here. All right. Then we walk along, we run into the wolf. The wolf gets half of what's left in our what? Basket. Well, if we look, our basket's currently divided in what halves, right? Because this is gone, that's what Mrs. P. So the wolf gets that third right there. All right, so then we walk along, we run into Mr. W, he gets 2/3. Well, what's left in our basket is what? This right here. We gotta what? Divide that into thirds. That's close enough to thirds. And Mr. W gets 2 of them, right? So Mr. W, Mr. W. And then we continue on, we walk along, we run into Grandma, and Grandma gets what? 6 jars, right? So what's left in my basket is what? Right here. So that is what? 6. What about this? 6 as well, right? Because these were thirds, and they understand unit fractions. They understand basic fractions, so that's 6, that's 6. 3 6s is what? 18. So that's what? 18. That's what? 18. And 3 times 18, well, 3 times 10 is 30. 3 times 8 is 24. And that adds up to what? 54 jars. Anybody come up with 54? Very good. Working backwards? Working backwards?
Yeah,
You did algebra?
You don't want to see my equation.
So yeah, so you can do, I like this problem because one, you can do guess and check. You could guess the answer and check it. You could guess 60 and find out that 60 doesn't work when you hit the Mr. Woodsman. Then you could figure out from there and so forth. You can use algebra. You can work backwards. I even built a little animation of working backwards, but I've lost it somewhere in all my videos. I don't know where it's at anymore. It's not labeled correctly. But you can work backwards and you can work what? Forward. So, and that day in class, most of the students actually did guess and check, which was a little disappointing for a math teacher to see guess and check as the primary method for a 5th grade math problem like this. So, all right, let's take a second look at another problem here. And I don't know if we'll get through all these problems, but I thought I would at least bring some problems here. Most of these are not out of the book. The book problems were much harder than I could do in a 45-minute presentation. And I didn't figure anybody wanted to see an induction proof today, so yeah. All right, so let's place 10 stools along the 4 walls in the room so that each of the 4 has the same number of stools. So see if you can solve this for me real quick as I erase some board space. All 10 along the walls, so each wall has the same number of stools.
Okay, the stool goes in the corner, does that?
Yeah, what is that?
How does a corner count?
Ah, step 1, understand the problem.
Oh.
We just had a good question. And the question was, how does the corner count? So if I put a stool in the corner, it counts on both, doesn't it? That's the key to understanding this problem. So if you go to this problem, you really just got to understand it a little bit. First off, you think, okay, I'll put 2 stools here, 2 stools there, 2 stools there, 2 stools there. And you guessed it, we decided we're going to solve this problem with what? A pitcher. And then, what's the problem? We still got 2 stools left. But if I put one in the corner, it's on both walls, right? So how many stools are here? 3? How many stools are here? Are 3? And then I would go over to this opposite corner. Then I have 3 there as well. So here's the interesting thing. Each wall has 3 stools, but we only have 10 stools total. Let that mess with your mind for a second. So, but there is the solution to that one. So this one, it really goes back to understanding the problem. You had to dive into that problem long enough to figure out that a stool in the corner counts as what? Both walls. All right, let's look at the next problem. Tanya walks from to school from point B from her house at point A. A distance of 6 blocks. For variety, she likes to try different routes each day. And how many different paths can she take if she always moves closer to B? So she starts at A, and we're going to move to B. So I'll give you a second to try this problem as I clear up some space. One more. Oh, thank you. That will definitely affect the answer. All right, so step one, we have to understand the problem. We're going to take different paths to school. And we can never go backwards. So we couldn't do something like that there because that moves us farther away. All right, so we're looking for how many different paths. So I think I got a pretty good understanding of this problem. And usually I like to write this down, but I got limited board space. All right, step 2, devise a plan. Well, it's pretty complicated to get from here to there on your own. Anybody try something smaller? Could we just figure out how to get to the next intersection? So step 2, devise a plan, as I'm going to break it into smaller pieces. And figure out how many ways to the next intersection. So I'm going to look at how many ways to the next intersection. Let me get a different color out here. All right, so we're standing here. Here we are. Visualize you standing there. We could go over this way, so there's one path there, right? We could go up this way, so there's one path there. Now, if I'm standing here, what could I do here? Well, I could go up, right? So there's one way there, or I could come across. So there's one way coming across. I could go up, so there's one way. So there's one way coming here, one way coming there. So how many total ways is there? 2 ways to that intersection. Then these 2 can come up. This one can come over. So that's 1 and 2. What does that add up to? That adds up to 3. All right, what about here? Well, I can continue on here. So there's one way there. Also one way there. And one way there. Remember, we're never allowed to go back. All right, these 2 can come over. This one can come up. So there's a total of 3 there. These 3 can come up. These 3 can come over. 3 and 3 add up to 6. These 3 can come over. This one can come up. So that's a total of 4 there. This 1 can come up. This 4 can come over. So that's a total of 5 there. This 4 can come up. This 6 can come over. So that's a total of 10 there. And 10 and 5 add up to 15 different ways. Do you want to trace them all out?
I tried that.
I'd go buggy. You'd go bug-eyed before you trace them all out. Although I've used this problem in class and had students trace out all 15 paths before. So then they were persistent. I would say they were definitely persistent. So, all right. Here's the only problem. We'll make this our last problem. Here's the only problem that's actually out of the book. A father is 3 times as old as his son. In 10 years, the father will be twice as old as his son. How old are they now? All right, we don't have a lot of time left. Could you do guess and check on this one? Could you guess an age and check it? Yeah. Anybody want to give me a guess? Well, nobody wants to guess. That's good because everybody wants to do some algebra. So step 2, devise a plan. Our plan is to do some algebra. Can't get away from algebra. So if we start off with F being, so remember, what was part of it? Introduce what? Suitable what? Notation. So we'll let F be the father's age. And we'll let S be the son's age. All right. So first off, a father is 3 times as old as his son. So I'm in step 1. I'm just writing down the given information, introducing what? Suitable notation. A father is 3 times as old as his son. So the father is 3 times the son's age. And then in 10 years, well, how old will I be in 10 years? I'll be F plus 10 or what? S plus 10. In 10 years, we'd add what? 10 on to their age. All right. The father will be twice as old as the son. So the father, well, his age now is F plus 10, so twice the age of his son would be 2 times S plus 10. And I'm sorry, I'm rushing this a little bit. We're almost out of the end of time. And so we'd set up this in equations. And so we introduce suitable notation. We set up an equation. Step 2, devise a plan. My plan is to what? Simply solve this equation. And the problem will basically set up itself. All I had to do is what? Introduce suitable notation and really just translate it into algebra. Well, let's solve it real quick. First off, I got 2 variables here, so what's the problem? I got to use a substitution. What's another name for father? Father is 3s. So we get 3s plus 10 equals, I'll distribute, I get 2s plus 20. Subtract 2s from both sides to get to the s. I get s plus 10 equals 20. Subtract 10, subtract 10. How old's the son? The son is 10. So how old's the father? The father is 3 times 10, which is what? 30. So, all right. So the 4 steps. The key thing on the 4 steps, let's get to there. The 4 steps provide a timeless approach to problem solving. It's not going to go with AI. AI is using the 4 steps. All right. By following the 4-step method, anyone can improve their ability to tackle problems efficiently. And I will say this, the book's target audience is not the average student. The book's target audience is really math teachers and those with a healthy appetite for mathematics. Because the problems in there were not basic ones. They were rather mathematical of type and a lot of geometry. So you really had to be into your geometry. And most of us don't take a rigorous geometry course like they used to take in the 60s and the 70s. So, all right.
What was the book again?
How to Solve It by George Polya. And so I'll show you the reference. There it is right there. It's 1945, Princeton University Press. So, and you're welcome to borrow mine if you want to read it. So, questions? Well, thanks for coming.
Thanks so much.